with this, talking about synthetic substitution. We were introduced to polynomials, talked about what they were, what they look like, how we can classify them, what the features are in a polynomial, leading coefficients, degrees, etc., etc. And then we ended up talking about this synthetic process, which ends up being really important. Synthetic substitution, which really is synthetic division, just without calling it that. And what this ended up being was a way for us to evaluate a polynomial without having to do exponentiation. Now, if we have a graphing calculator available, if we have a graphing calculator available, then there are some easier ways to do this. For example, let me just pull one up here and show you a couple tricks, remind you about a couple tricks. Okay, so if we want to evaluate this polynomial at x equals 3 or any other value of x, one thing we can do is we can just plug in the polynomial. We can enter it in terms of x's. So I could say 2x to the 4th plus negative 8x squared would just be minus 8x squared plus 5x minus 7. And then if I hit enter, I'm going to get back probably some gibberish answer. Now that's just based on whatever the last value of x was that was stored in the calculator. And who knows why? It might have been from a graph. We don't know. But whatever it was, when I plug it into that expression, that's the answer I get. We don't care. We want to plug in 3. So what we're going to do is we're going to put 3. We're going to hit 3 and then STO for store as x. Hit enter. And then now x equals 3. So we'll just go back up and grab our expression, highlight it and hit enter. And then we'll hit enter again to evaluate it at x equals 3. And that's our answer, 98. Okay. So if we wanted to plug in another x value, what if we wanted to plug in x equals 77? We could do that. We could hit 77, store x, enter, and then just go right back up and grab the expression and hit enter to evaluate it. And then we get some enormous number. Okay? But that's it, that's the answer. That works really well. That's an easy way to evaluate expressions or functions. There's another way that's also pretty easy. If we go to y equals and we enter this expression as y1, then if we go to the table, if we hit second table, I had pushed it down to some negative values, but it's going to give us a table of values, x values, and the corresponding y values. So if we go through this thing, if I get a bunch of values in a row that I want to use for x, for example, this is a good way to do it. Like let's say I wanted to know for 5, 6, 7, 8, and 9 what the values of the function were. Well, there they are, right there. Okay. So that's another real convenient way to do lots of evaluations of a function. Okay, but what if we don't have a graphing calculator available, like on the graphing calculator test? Yes, ma'am.
So, like, if we were like in algebra and we wanted to find no, like the regular, freshman algebra.
Right.
We would just put it, go, like, we don't go with what I was in there, and then we could do the same thing and like, give us the little table.
Yep. Yeah. How about that? Okay. Now, what if we don't have a graphing calculator available though? Then it gets to be a lot harder to evaluate because we've got these big powers of x sometimes, right? And that's the part. It's not the multiplication and addition that's hard. It's the exponentiation that's hard. But if we use synthetic substitution, we don't have to do any exponentiation. Then it's all just multiplication and addition. That's it. Remember how we did this? If we write out our polynomial where we show all the coefficients, even zero coefficients. So if we skip a term, we're going to write that as a 0 times that power of x, right? If we pull all those coefficients down in order from the leading coefficient all the way down to the constant, then we'll make our little synthetic bracket, And whatever the number is that we're plugging in for x, recall, it goes out front. Okay? And then we just do the synthetic process over and over again until finally we get down to the box. The number in the box is going to be our answer. So bring the 2 down. 2 times 3 is 6, which we add to the number in the next column. So plus 0 is 6, times 3 is 18, plus negative 8, 10, times 3 is 30, plus 5 is 35, times 3 is 105, plus negative 7, well, there's our 98. Okay. So that works also. That works really well if you don't have a graphing calculator. Okay, the rest of the stuff here. The other thing they talk about is end behavior. And the way the book does this, I really sort of object to. They're going to give you a table that you can sort of memorize and then know what the signs are, but that doesn't really work well because you're just going to forget it. Anything you memorize, you will forget. I want to show you a better way of doing this where you just look at you can just evaluate the sign of the first term, the leading term, and that's all you need. So what we're doing is when we calculate end behavior, we're trying to find out what happens to the value of the function as x approaches infinity or negative infinity. That's kind of weird stuff. So in other words, what's going to happen if I were to draw a graph? What's going to happen as we push the function way out to the right in the positive x direction? What's going to happen to the function? Or what's going to happen to it if we push it way off to the left in the negative x direction? Think of it as an ant. If an ant's walking out infinitely far to the right, is he going to be climbing up a function infinitely high or dropping down a function infinitely low? One or the other. It's going to happen with a polynomial, always. Which one? Well, the way we find out is by looking at the leading term. Let's take an example here. If we look at some real simple functions here at first, let's just look at these graphically, and then we'll see that it's easy to tell graphically. The picture tells us what's going on. But it's when we don't have a graph, that's what gets a little trickier. What if we take the function f of x equals x, y equals x? As x approaches positive infinity, and that's a weird way to say that, but the reason we have to say approaches is because you can't ever get there. Infinity is not a number. It just means going without limit in the positive x direction. So if the ant goes forever in the positive x direction, what's going to happen to the function? Well, we can see here that he just climbs upward forever. And so f of x, which just means y, also approaches infinity. Right? So as x approaches infinity, f of x approaches infinity. What about as x approaches negative infinity? Meaning as the ant walks in the negative x direction forever along the function. What's he doing? Well, in this case, we can see that he's walking downhill forever. And so as he does that, as x approaches negative infinity, the function also approaches negative infinity. We can see it on the graph, right? A lot of times we call this, it's end behavior, but we call it we want to know what's going on at the tails of the function, we'll say in math sometimes. Way out there, what's it doing? What about this simple example? If f of x equals negative x, so now we've got a downward sloping line. Now we get the opposite happening. As x approaches positive infinity, we can see that f of x is approaching negative infinity. It's going down forever. On the other side, as x approaches negative infinity, f of x is climbing up to positive infinity. But if we look at parabolas, you can see the same kind of thing happening here. If we take f of x equals x squared, sort of our normal parabola, as x approaches positive infinity, y approaches positive infinity, right? Climbs up forever. As x approaches negative infinity, y approaches positive infinity in that case also. And we can look at more examples, but you get the idea. With a graph, it's pretty simple. Now, what if we don't have a graph? Okay, we're going to skip all this stuff. We don't want to do that. What about this one? Okay, let's take this example. We want to know what's going on here as x approaches the end behavior. As x approaches positive infinity, what's f of x doing? And as x approaches negative infinity, what's the function f of x doing? Well, let's look at this for just a second here. Let's just talk about the function. Now, every place I have an x, wouldn't you agree that as x gets infinitely big, for example, this first term is going to get infinitely big, right? That second term is going to get infinitely big, and the third term is going to get infinitely big in a positive or negative way. We haven't specified that yet, but they're all going to get infinitely big, either positively or negatively, because they've got x's in them, right? If I multiply by a number that's getting infinitely big, well, the answer is going to be infinitely big. So it seems as though, when we first look at this thing, it seems like, well, how do you know? We've got all these things going on. I've got these first two that seem like they're going to be positive. Minus 4 times a really big positive number is going to be negative. Which one wins? Which term wins and determines what actually happens? Any suggestions? Because there's a definite answer. One of them does win. What do you think? Which one is going to be the most? Well, let's take some big numbers and see which one's most aggressive here. What if we take the number x equals 100? Negative 1 gets left in the dust. It just stays as negative 1 because it's a constant. Negative 4 times 100 is negative 400. That's pretty big compared to negative 1, right? X squared becomes 10,000. That dwarfs the negative 400, right? But x cubed becomes 1 million. So that's clearly the one that's growing the fastest, right? And the bigger the value of x gets, the more extreme the difference gets, right? So now let me ask you again, which term wins? Which term is going to contribute the most to what's happening as x gets really big? Yeah, the biggest power. The first term, the leading term, equals the dominant term. It's the one that's going to make the most difference. And here's a way to think about that. It's a little strange conceptually, but it's not hard in practice. We'll talk about this more in years to come. But think about this now. If x is approaching infinity, then x cubed is like saying infinity times infinity times infinity, whereas x squared is like saying just infinity times infinity. Now there's a difference there. They're both getting really big, but the first one is doing it infinitely faster than the second one. And so for that reason, these other terms we don't care about. They're going to be left in the dust. It's only the first term that matters. So that's the only one we have to look at. Now we always know, from the very beginning, we know that as x approaches positive infinity, for example, we know that f of x is approaching some kind of infinity. The question is just, is it positive or negative? We already know it's infinitely big. We just have to know the sign. So all we have to do is just look at the sign of the leading term, the dominant term. If we look at the dominant term here, the dominant term is 1 times x cubed, isn't it? There's an invisible 1 out front. We always want to look at, we want to consider the coefficient and then the power of x. So 1x cubed, as x approaches positive infinity, what's the overall sign going to be? Well, 1 is always positive. If f of x, as x is approaching positive infinity, x is a positive number, right? If I take a positive number to any power, what's the sign going to be? Positive. So I end up with a positive times a positive, which is what? Positive number times a positive number is positive. So I get a positive infinity for my result. That's the limit of the function. As x approaches positive infinity, f of x would approach positive infinity because of the sign of the first term. Now what happens as x approaches negative infinity? F of x approaches what kind of infinity? Well, let's check the sign. As x approaches negative infinity, 1 is still positive, but what's going to happen to x cubed? As x approaches negative infinity, well, that's a negative number. A negative number cubed. In fact, a negative number to any odd power is what sign? Negative. So I end up with a positive times a negative, and what do I get from a positive times a negative? A negative. So that's my answer. So you see that answer? No big deal. Just look at the sign of that first term, and that's going to tell you what kind of infinity we're dealing with. What about this one? Look at this one. One last example. As x approaches positive infinity, f of x approaches what kind of infinity? Just look at the first term only. There's my first term. Okay? I'm going to get, if I look at that first term, I've got a negative 1 times an x to the 4th. So, as x approaches positive infinity, my signs are going to be negative times positive number to the 4th is positive. What is that? Negative. As x approaches negative infinity, what's going to happen? Well, if we approach negative infinity, we're going to get negative 1, which is negative. A negative number to an even power is positive. So I end up with negative infinity, negative times positive. Okay? That make sense?
Yeah.
Okay. Yeah. Much easier than having to memorize that table. That table is just doesn't seem like a good way to do it. That's it. Yeah. All right. So we can find a left.